We're now going to turn our attention to two-stage completion stage methods. These are ones that will be triggered when both of two previous stages complete. So this is the conjunctive or and variant. So this particular approach will have several methods. We'll start by talking about one known as then combine, which will be triggered when both previous stages complete successfully. And I like to think of this as kind of like merging lanes, right? You have two lanes that come together into one lane. That's kind of the visualization I have in my mind when I think about then combine. Then combine applies a bifunction action to both results from the previous stages when they complete. So you can think of it as logical conjunction. It's the and operator, and it takes a bifunction. Two completable futures are used here. One is the one that's used to invoke then combine. So if you say, completable future one dot then combine, that's the first one. That's this, if you will. And the other one is passed in as a parameter to then combine. That's the first parameter. That's the other. It's called other. And so those two have to both finish before the function is run. And it returns a future that contains the result. It returns a completable future to the results of applying the bifunction action. You can think of then combine as essentially performing a variant of a reduction. If you think about the collect method, for example, or the reduce method, you're reducing things. But in this case, we're just reducing two things to one. So it's like two streams coming together or two lanes merging. It's typically used to join two paths of asynchronous execution. And here's one of my all-time favorite examples, which does several things. It shows how to use the then combine operation in completable futures, and it also demonstrates what you can do with the abundance of cores that now exist in modern multi-core processors. So you undoubtedly remember when you took your sorting section of your algorithms class, assuming you've taken that, or you've probably even talked about some of this in the data structures course. If you recall, there's a bunch of different sorting algorithms. There's quick sort, there's heap sort, there's bubble sort, there's merge sort. There's probably 20 interesting sort algorithms that you probably have been exposed to at one point along the way or another. And one of the age-old questions is, which is the best one? And the theorists will spend enormous amounts of time analyzing the runtime complexity, and they'll talk about the adversary, and certain sorting algorithms work very well if the input's almost already sorted. Other ones can be made to be pathologically inefficient if the adversary arranges the data in a certain way, like quick sort, unless you do all kinds of heroic things to it. The point is that we never are quite sure which sort is the best. So rather than spending our lives doing theoretical analysis of things, let's just take advantage of the proliferation of cores, and we'll run a bunch of algorithms in parallel, and whichever one finishes first will take that result. So that's one way to think of this. This particular approach is going to use a variant of that, where we're going to go ahead and multiply big fractions together, and then we're going to divide other big fractions. And what we're going to end up with when all is said and done will be results, and we want to combine them together. So again, this is a way of taking advantage of all the cores that we've got at our disposal. So we're going to go ahead and run this computation in one thread, which will be mapped to one core. That's the multiplication one. We're going to take another computation and divide it. And then when both of those computations are done, then we're going to take the results and we're going to add them together, and we'll print the results out. So then combine only runs when the other ones work. So we start by doing asynchronous multiplication and division of big fractions. When both of those are done, and only when they're both done successfully, then we add the results together, and then we go ahead and print the results. So it's a way of taking advantage of all the cores that we've got. We can do all these computations in parallel, and then when they're all finished, or both finished in this case, we can go ahead and sum them up. We'll see there's other cool variants of this later when we talk about arbitrary arity methods. So that's the quick overview of the two-stage completion stage methods where we wait for both of previous stages to finish. That's the AND version.